The next talk that we have, this is one of the submissions that was accepted for an oral presentation. So I've got Sikon Wong, who's going to present this.
Okay, hi everyone. My name is Sutong. I'm a PhD student at UC Santa Cruz. I'm presenting our paper, Context Models and Prompt Optimization for Automated Hallucination Detection in LLM Output. And my co-authors are Jincheng, Shigen, Karthik, Arkachoti, and our advisor, Ian Lane. I'll start by introducing what hallucinations are and the semi-eval task that we participated in which that aimed at detecting hallucinations. Then I'll introduce our system and its performance and results on the task. And then finally, I'll conclude by sharing some insights and takeaways. To begin with, hallucinations in the LLM space is quite an overloaded term, but here's a definition that works for most of the cases. We can define it as LLM-generated outputs that are fluent and confident sounding, but factually incorrect, unsupported by the input context, or inconsistent with real-world knowledge. Given the definition, it is a well-known problem that LLMs can hallucinate, and this is especially true when using LLMs to answer factual, knowledge-intensive questions. Thus, there is a need to find out where they hallucinate, and deciding whether an answer contains a hallucination somewhere is relatively straightforward, and that's what most existing systems do. That is assigning binary labels or even a score to a generated answer. However, being able to pinpoint at the span level exactly where in the answer the hallucinations is would be much more useful. Having this span level information is beneficial to both the end users and model developers. Users can be informed of where the answers could be unreliable and might require a second look. And engineers can use the highlighted spans as additional fine-grained signals for training to improve the model. Now that I've motivated why detecting hallucinations at the span level is important, one of the shared tasks at semi-eval this year was doing exactly this. The task MUSHROOM, which stands for Multilingual Shared Task on Hallucination and Related Observable Overgeneration Mistakes. The task essentially challenges participants to detect hallucinations of LLM-generated answer down to character precision. The problem is set up like this. Given a question and an LLM answer, detect the hallucinated spans in the LLM answer. And here is a more concrete example. The question asks, what did Petra van Staveren win a gold medal for? And the LLM answers, Petra van Staveren won a silver medal in the 2008 Summer Olympics in Beijing, China. Okay, this is a concise and to-the-point answer, except that in reality, she won a gold medal in the 1984 Summer Olympics in LA. Of course, the task is just to find these spans like these in which the model hallucinates. And in addition, the task also asks to do this in 14 languages. The predicted spans are then evaluated with a character intersection over union, or IOU. It counts the sets of characters in the intersection of the ground truth and the predicted, and divide that by the count of their union. So in this example, the IOU is computed as the intersection between the gold labels, gold label spans, and the predicted spans. So the intersection of characters is 24. It's 24 characters, and that is divided by the union of these, which is 60 characters, and that gives the IOU of 0.4. Thus, IOU measures how well the predicted hallucination regions align with the ground truth ones, penalizing both the missed detections and false alarms. And next, I'll introduce our system for this task. Our system follows a three-stage framework. We first do context retrieval. That is, we retrieve relevant context that is helpful for answering the question, and which is then followed by hallucinated content detection, where we detect the hallucinated content based on the retrieved context. And then the final step is spam mapping. Here we map the hallucinated content back to the spans in the answer. In the first context retrieval step, we retrieve relevant context that should be helpful for determining the truthfulness of the answer. And here are two ways to do it. Either use the question directly as the query, or use the claims in the answer and query for information that can fact-check the claims. And next, we detect the hallucinated content, so detecting hallucinated content detection, and then map them back to the spans. Since these two steps are tightly coupled, I'll talk about them together. Here we have three different methods. The most straightforward is text extraction. That is, given an LLM the question, the context, and answer, and prompted to output the hallucinated spans. And then to map these back to the answer, we do a substring match against the original answer. And another way to do this is to parse the context into a knowledge graph and break the answer down to individual facts. Then we verify each fact against the knowledge graph and use an LLM to map the false facts back to the spans in the answer. Finally, the last approach is minimum cost revision, where we use a reasoning model such as O1 at that time to correct the answer with the minimum number of changes. Then we do span mapping by computing the edit distance from the original answer to the corrected answer. The tokens that were marked as substituted or deleted are considered to be hallucinated. And here is a full diagram of with all three steps shown. As an additional step, we also applied automatic prompt optimization to the text extraction approach. We used the MIPRO V2 optimizer with DSPy to search for a prompt that will maximize our task metric IOU. And now I'll get to our results. So our main results can be summarized in this table, which is evaluated on the English test set. Firstly, context is king. Including the retrieved context is extremely helpful, which boosts our IOU score by 27%. And secondly, simplicity wins. Our simplest method, text extraction, that is prompting the LLM to extract incorrect spans based on the context, it consistently outperforms the other two more complex approaches. And thirdly, complexity didn't really pay off. The knowledge graph verification method performed the worst by a wide margin, with its IOU score dropped to about half of the other two methods. While it could identify false facts with the knowledge graph, it was extremely unreliable at mapping those errors back to the correct text spans in the original answer, which severely hurts its performance. And lastly, minimum cost revision was competitive but costly. It was a strong performer, achieving 0.53 IOU. However, this approach came with a significantly higher computation cost due to the reasoning required. And here's our results across 14 languages. In the previous slide, I mentioned the complexity with knowledge graph didn't pay off, but this time prompt optimization did pay off. It boosted IOU on 9 out of the 14 languages. And our system achieved top 50s or 60s on most languages, which placed our system in the top 2 for 11 of the 14 languages. And finally, we get to conclusions and some takeaways. First, we proposed a 3-stage system for detecting span-level hallucinations. And we found that context retrieval is a crucial first step for hallucination detection, and contexts that cover the answer but not too verbose work the best. We also found that simple and well-prompted, such as prompt-optimized system, can be more powerful than more complex systems, such as knowledge graph. In addition, the authors, manually annotated the validation set and found that our system can outperform our best annotator by a large margin. Our best system achieved 0.57 IOU, whereas our best human annotator only achieved 0.48. And that brings out the last point. This task is inherently ambiguous. It is challenging to define a single correct hallucinated span and have all annotators agree. And thus, we need to be more careful when designing evaluations for hallucination span labeling. And that concludes my presentation. I'm happy to answer some questions.
Okay, I think because we're running a little bit late, why don't we take questions during the break? And I want to thank Sukong for the amazing talk, really interesting results, really important for all of us. Thank you. Let's thank him again, please. Thank you.